Alright, so today guys, we're going to actually derive the definition of a derivative formula, which I've already written out right here. So we want to understand where does this formula come from visually from our graph. Now, a derivative by definition, well, verbally, is just the slope of a line that is tangent to the graph of our function. Now, before we actually derive this formula, we're going to go back to algebra and find out just basic slope, which I'll denote by m. What is slope? Now, verbally, slope is just a measure of the rate of change, as in, as my x value changes by a certain amount, how does y change directly? So, but mathematically, slope is defined as the changes in our y over the changes in our x, which you should already know. So if I had 2 points, one over here and one over here, and the coordinates at this point were, let's say, x1, y1, and the coordinates at the second point were x2, y2, then my slope would be the difference in the y values, y2 minus y1, over the difference in x values, x2 minus x1. And this is the basic definition of slope, and you may already see or may not, but these two are essentially the same thing, but in a specific situation for derivative, where our x2 begins to approach x1 so that they are essentially overlapping the same point. That's okay if that doesn't make sense right now. We're going to look at another example. So, say we have this curved line. Now, before in the previous example, we had a straight line, so the slope was consistent and constant, and it didn't matter. But when you're dealing with a curve, the slope at this point is not the same as the slope at this point. But say we wanted to know at a specific point exactly what that slope was, well, then we would need to know what is the line tangent to it, and then the slope of this line will represent the instantaneous slope at that exact moment. And this varies as we move along, as you can see right here. So, say we wanted to know the slope at this exact point. Well, for finding slope, we need 2 points because it's a rate of change. Now, if I had another point here and another point here, the coordinate at this point, let's say, is a distance x from the origin. So then our x coordinate, or in the horizontal, would just be x. Now, what would our y value be? Well, y I've written here is just a function of x, so it depends on whatever our x value was at that point. Well, at this specific point, our horizontal value was just x, so our y value will be equal to whatever happens when we plug in x into our function for every other x value. Now, at this point, let's say the second point relative to our initial point is a horizontal distance h. Then that means the distance from the actual origin for our second point would be equal to x plus h. So then what would x coordinate be? X plus h. And our y coordinate, well, y, as we said, is a function of x. So since our x value or horizontal value at this point is x plus h, our y value will be dependent on what if we plug in x plus h into our function. So we have 2 coordinates already. So if you have 2 coordinates, you can find slope by finding the changes in y over the changes in x and the differences. So if we find the slope of this, we would get that y2 minus y1 over x2 minus x1 is the the generic formula for slope. But what actually is our y2 value and our y1 value? They're right here. So we have f of x plus h minus f of x over, now our x2 and x1, we have x plus h minus x, and if you can already see that we can cancel out positive x and negative x, so that we just get the slope is f of x plus h minus f of x over h. Now what is h again? As we saw earlier, h is just the distance that our second point is from the initial point. Now, if you're trying to find the slope of a line that is tangent to our initial point, that means that these 2 points must approach each other so that they eventually overlap into a single point that this line crosses. Now, in order to do that, what must our distance h be from our initial point so that these 2 points are essentially overlapping each other? Well, that means the second point must be directly on top of it, so our h would actually be equal to 0 at this point. Now, as you can tell, if you want to know the slope of that, you'd think you'd assume and plug in 0, but you can already see that plugging in 0 would make this function undefined. So we're not going to do that. However, that's the reason why we have limits, because limits allow us to, instead of plugging in a value directly into our function, we could kind of, if we were to look at all the tangents of all the slopes of this line from the first initial point and we slowly made that second point approach the first, then we would find that the limit of h approaching 0. Remember, h is the distance from our initial point. So as h approaches 0, it gets closer and closer to the same point, and our line goes from intersecting 2 points in our function to eventually becoming tangent and just intersecting 1. And this overall is now our new derived function, and this is all you need to know, that this is the derivative, the definition of a derivative, and that is how you visually prove it.